Hi,
Hello,
in
the
this video
microphone
I
should
would
be
like to
working.
present the
It
basic
should be working.
ideas related to frequency response from a mathematician's point of view. All right. So first of all, imaginary exponentials correspond to sinusoidal oscillations. More specifically, the imaginary exponential f of t equals e to the j omega t. Now, engineers use j instead of I for the square root of -1. And you're considering this exponential, imaginary exponential, as a function of time. This w is at omega. It's commonly used for angular frequency. I'll explain angular frequency in a minute. Right? So we have this imaginary exponential, e to the j omega t, function of time. Omega is the angular frequency. J represents the square root of -1. We can also write it this way. You might also have seen this as cis omega t. So this corresponds to a sinusoidal oscillation. As time varies, the real part and the imaginary part both vary sinusoidally. Right? Cosine you also call a sinusoid, right? Basically the same as sine, but it's offset by a phase. Right? So angular frequency is 2 pi times the regular frequency. So angular frequency is measured in radians per second. And regular frequency is measured in cycles per second. So when you think about going around a circle, right, it goes around 2 pi radians when it makes one cycle. So that's why the angular frequency is 2 pi times the regular frequency, because there are 2 pi times as many radians as there are cycles. So regular frequency is measured in cycles per second. Sometimes it's called hertz. So I can put that in. It's also called Hertz. Hertz was a physicist. But 1 full cycle is 2 pi radians. Okay, so the real part of e to the j omega t is cosine omega t. Imaginary part is sine omega t. So we showed that up here already. So we have an equation involving complex exponentials. Both the real part and the imaginary part of the equation make real sense. You can look at just the real part or just the imaginary part, and they both make sense. Actually, they're offset by a phase of pi over 2. Now, the complex equation is often simpler than the real or imaginary part. So that's why electrical engineers work with complex equations. You don't have to deal with cosine and sine. You just have this imaginary exponential that gives you both. And at the end of the day, when you want a real signal, you simply take the real part of your complex signal. Right? Now, consider a continuous system, I should say continuous time system, which corresponds to a linear differential operator, or I should say to linear differential operators, because I have more than one. So, I should say here which is specified in terms of. Okay, so it has the form Ly equals L prime x. So in this case, x is the input and y is the output. Sorry. X is the input. And y is the output. And L and L prime are linear combinations of derivatives. I shouldn't put ddx here. I should put ddt, because typically we're thinking of these signals as functions of time. This is just one example of a linear differential operator. I could have higher order derivatives, and I have derivatives on both sides. Okay. So here I can say this is one possible example of a linear differential operator. There are other possibilities. Okay. Then the response of the system, I should say the system, to an exponential function x of t equals e to the st is a constant multiple times the same exponential function. Now, s could be real or complex. It doesn't matter. That's the wonderful thing about complex numbers, is he puts the real and the imaginary on the same footing. And the math still works. And like I said, at the end of the day, you still have a complex equation. You can take the real part, and it makes real sense. Now this constant multiple, I should revise this. So the constant multiple is given by taking the Laplace transform of the equation, this equation here. Okay, and what does this do? This replaces the derivatives. It replaces each time derivative with a s. Okay, so each time derivative is replaced with an s, and we get an equation of the form. The Laplace transform of y is equal to some polynomial in s times x of s. So in fact, the constant multiple that is basically the characteristic multiple, we can call it the gain of the system. So what did I call it? G of s, because G for gain. Okay, so the constant multiple that I referred to in part 2 is given by this G. So you can see that G depends on S, but there is a very simple procedure for finding the constant multiple. Just replace the derivatives by S, and then the Y and the X you don't really care about. Those are just going to be symbols, but the derivatives will be replaced by polynomials in S, and you simply take the ratio of these two polynomials, and that will give you G. All right, now what about frequency response? Well, if S is a imaginary number, then the imaginary part corresponds to the angular frequency. Beautiful thing. That's the same thing we do with real exponents. Real exponentials we can do with complex exponentials. And, so we get so if you feed in a frequency into the system, this is telling you what will happen in the output, what happens to that output signal. Okay. Now, the frequency response in general is a complex number which can be expressed in polar form. Now, it's a complex number, but it has a real interpretation. The modulus of the frequency response is the amplitude of the response sinusoid. In other words, if the frequency response has amplitude 2, then your signal is going to be amplified by 2. And the phase of the frequency response is the phase of the output relative to the input signal. Okay, so let me see. It's phase of output. So really all this does is reduce to mathematics of complex numbers and complex functions. But you want to relate these complex equations to real signals. And we'll talk about that when we look more in depth in the homework.